Yeah, thank you, Ben, for your kind introduction. Yeah, I'm Jian from Utah State University. Today I will introduce one piece of my recent research about the electrochemical synthesis. Yeah, right now I'm a postdoc in the Department of Chemistry and Biochemistry at Utah State University. Actually, my research are in the overlapped range between of the chemistry and the material science. I'm developing the redox active materials for the energy storage and the catalysis. Specifically, we developed the redox active materials for the energy storage. For example, the redox moleculars for the aqueous organic redox flow batteries. For example, we developed a series of biologen moleculars or the fluorescent-based moleculars. Use these organic moleculars as the active material for the energy storage. And we also developed advanced magnesium electrolytes for rechargeable magnesium batteries. In the catalysis field, we also developed organic redox materials for the photosynthesis and the electrosynthesis. Here today, I will talk about a piece of work in the last part, the electrosynthesis. When we're doing the redox active material development, we found that the nickel bipyridine complex itself in the organic solvent, it showed very reversible redox behaviors. But when it meets the aryl halide, for example, if we add the aryl bromide into the reaction mix, into the solution, we will see the reversibility loss of the nickel bipyridine complex. For example, this one, you can see after in the presence of the bromobenzene, the reduction peak get increased. However, the return peak disappeared. So we believe what happened is once the nickel complex was reduced from nickel 2 state to nickel 1 state, the ligand may dissociate and give empty states. When there is empty states, the no-valent nickel species, maybe nickel 1 or nickel 0, can react with the aryl halide to through the oxidative addition reaction. So we want to make use of this cathodic half reactions to develop some useful coupling reactions. And for the electrosynthesis cell, there are 3 types of cell configurations. The first type is called unpaired cell. In this cell configuration, the substrate was electrochemically reduced or oxidized at this electrode and to generate an intermediate. And the intermediate goes through some chemical process to produce the final product. So here is the CE process. That means electro and the chemical process. The advantage of this cell configuration is it is straightforward, so it is very easy to design the reactions. But the drawbacks for this cell configuration is it needs the sacrificial reagent or sacrificial reactions to balance the charge for the overall reaction. And the reaction scope of this kind of cell configuration is limited in the pure reduction or pure oxidation reactions. And because the sacrificial reaction not only consume chemicals, but also will waste some of the energy. So the overall energy efficiency for this kind of cell configuration is not high. The second type of cell configuration is so-called sequential paired cell. So under this cell configuration, the substrate was first reduced on the surface of the cathode to generate intermediate 1, and the intermediate 1 will convert to intermediate 2, and then oxidized to intermediate 3, and finally produce the product. It can also be first oxidized and then reduced. The advantage for this kind of cell configuration is it is redox neutral, so we do not need any sacrificial reagent to balance the charge. But the drawbacks for this cell configuration is the reaction is kind of complex because it first need to be reduced in the cathode and then migrate to the anode and do the electrochemical oxidation. Then the reaction is very hard to design, and also the reaction mechanism study is not convenient. The third type of cell configuration is called convergent paired cell. Under this cell configuration, one substrate was reduced at the surface of the cathode to generate intermediate 1, and the second substrate was oxidized at the surface of the anode to generate intermediate 2. And the intermediate A and 2 will react with each other to generate intermediate 3. The intermediate 3 further convert to the final product. The advantage of this cell configuration is the anode half reaction and the cathode half reaction and the anode half reaction is independent. So we can divide it in design those two different half reactions and combine them in a cell to get the overall reaction happen. But the challenge for this kind of cell configuration is it is really hard to get the anode and the cathode half reaction match to each other. Yeah, for those two redox neutral cell configuration, or we can also say it is a paired cell configuration. The challenge is mainly raised from the reaction kinetics and the stability of the intermediates and the mass transport, because the mass transport is very important in those two cell configurations, because usually the intermediate is not very stable. So if the mass transport is low, there is not enough time to get to make the reaction happen, and the intermediate already quenched. So that is the challenging part for this kind of paired cell configurations. And based on the advantages and the disadvantages for those three different types of cell configurations, we decide to use the third type of cell configuration to develop our new reactions. The reaction we designed is next here, showed here. At the cathode site, the nickel-2 species will be electrochemically reduced to nickel-1 or nickel-0. And those no-valent nickel species can oxidative addition with a halide to generate this intermediate. And at the anode side, the substrate will be directly electrochemically oxidized and decomposed to generate a carbon radical here. And this carbon radical can bond to the nickel species through a single electron transmethylation to generate this high-valent nickel intermediate. And this high-valent nickel intermediate undergoes reductive elimination to get the CC bond formation and recover the nickel catalyst. This is our reaction design. And we want to figure out what kind of anodic half reaction and cathodic half reaction is good for this kind of cell configurations. So we conducted the CV screening. For example, we use different types of carbon halide bond as organic halide as the electrophiles. For example, we use sp3 carbon, sp2, and sp carbon, and different types of electrophiles. And also the andesite, we tried the carboxylate and the trifluoride borate as the nucleophiles, different types, for example, the sp3, sp2, and sp. Yeah, this side we use the nickel as the catalyst. We want to see what kind of electrophiles is reactive for the nickel catalyst. Actually, we can see the green curve. This one, the aryl bromide, showed the best reactivity for the cathode side half reaction. And for the anode side, we can see this trifluoride borate. This sort showed the best electrochemical activity as the anode. So we first we focus on those two substrates, and then for the optimized reaction conditions, we secondly we scanned the ligand. We tried different types of bipyridine ligand and the terpyridine ligand. And we can see here the green curve. When we use the butyl bipyridine, it showed the best reactivity for the oxidative addition. And the 2,2-bipyridine, this one also showed kind of reactive for the oxidative reaction. And this side, we tried to study what's the ratio of the nickel metal and the ligand gives the best current response. We can see 1.5 equivalent of tert-butyl-pyridine showed the highest current response. So we tried to we focused on the tert-butyl-bipyridine as the ligand, and here is the optimized reaction condition. You can see use the tert-butyl-bipyridine and the nickel diagram as the catalyst, and aryl bromide as the substrate and cathode side substrate, and the trifluoroborate as the anode side substrate. It, based on the CV study, it showed the best result. And we directly tried the reaction, use these combinations. For example, we use 1.5 equivalent of borate substrate and 1 equivalent of aryl bromide. Use 10% more of the nickel chloride glam as the percanist. Tert-butyl bipyridine used 15% more as the ligand, and potassium carbonate as the additive in the DMF. Using lithium chloride as the supporting electrolyte, we can get 93% yield of this desired CC cross-coupling product. We also find about 5% product of this CC homocoupling product. And we use different base, different supporting electrolyte, and the different current intensity. We found those different conditions showed significant influence on this negativity between this cross-coupling reaction and the homocoupling reaction. Then we extended the scope of the substrate. For example, we tried the chloride as the electrophiles. It showed a slightly lower reaction efficiency than the bromide. It is because the chloride is less reactive than the bromide for the oxidative addition. Especially, you can see when the substrate is the electron donating group substitute chloride, the yield is much smaller than the bromide. And when it is the bromide substrate, we tried a lot of different function groups. This reaction system showed tolerance to a broad range of the functional groups. For example, the bulk group or the this kind of protecting groups. Also, the heterocycles also showed efficiency for this reaction, but the yield is slightly lower. It may be because of these nitrogens can also coordinate with the nickel, so it makes the reaction more complex, and the reaction efficiency will be is relatively lower. We also tried different benzyl trichloroborate substrates. We tried the electron donating group functionalized substrate, electron withdrawing substrate, and also this one you can see if the alpha set was functionalized with an oxygen. This oxygen can stabilize the carbon radical here, and this kind of substrate also showed some reactivity for this reaction. We get about 50% yield. And in the CV study, we also found that the beta bromoserine, this kind of sp2 carbon inite, can also show some electrochemical reactivity for the nickel-based oxidative addition. And then we also tried this kind of substrate in the cross-coupling reactions. However, because this kind of substrate, it is the steric hindrance is smaller than the bromide. So when we use the filter bipyridine as the ligand, we get a large amount of this homocoupling product, and the cross-coupling product we only get 48%. But when we use the pyridine to replace the bipyridine, we can get very good yield. It is more than 80%. And when it combined with different borate substrate, all of them showed a very good reaction efficiency. With this optimized reaction in our hand, so we want to demonstrate the application of this reaction. For example, we use these electrochemical reactions to synthesize some pharmaceutical compound. For example, this one and this one, we use our reaction to do the key steps for the construction of the final product. And we also did the late stage functionalization of the pharmaceutical compound and the bioactive molecules, and generate a series of brand new chemicals. We also used our redox flow battery to demonstrate the off-scale synthesis. For example, these molecules, we use the flow cell demonstrate 3-gram scale reactions. Here is the room-in of the flow synthesis setup. It contains 3 steps, 3 parts. The first part is this tube, plastic tube. it is a reaction mixture, a reaction solution reservoirs. We keep the solution in this tube, and the middle part is a pump. We use a pump to push the solution into the electrochemical cell at this side, and then when we connect it to the potential state, and the pump will push the solution and circle in the reaction loop, and the reaction will happen on the flow cell. Yeah, this is the reaction between the triphenyl borate and the arahalide. And previously in the CV screening, we also tested different nucleophiles and electrophiles. So once those combination will happen, will they work? We also tried. For example, when we use combine this SP carbon bromide and this borate salt, do the reaction under the standard condition. However, because this bromide is not stable, so during the reaction, this substrate already decomposed, so we did not get any cross-coupling product. And the benzyl carboxylate in the CV also showed some reactivity at the anode side. We also tried to use it as the nucleophiles combined with a stronger base, cesium carbonate. We can get 18%, 17% yield of the cross-coupling reaction, but the main product is the homocoupling product of the arabromide. And when we use this tubular carboxylate as the substrate, there is no reaction happened. Under this condition, it is mainly because after a couple of minutes, the cell voltage will increase to very high, so the reaction cannot keep going. And if we use this benzyl borate as the substrate, under the standard condition, we can only get the homocoupling product of this arahalide. And if we use this sp3 carbon chloride as a substrate, we did not get the cross-coupling product. We only get the homocoupling product of this borate as the product. So actually only this carboxylate showed some efficiency for the desired cross-coupling reactions. The other combinations seems does not work under these reaction conditions. Yeah, for the reaction mechanism study, we first did the CV study for the cathodic side. You can see the gray curve is the CV of the arabromide, this one. It showed a reduction, irreversible reduction signal at more negative than -2 volt. And the bipyridine ligand, it showed a reversible redox peak at about 2.7 volt. Yeah, the combination of the bipyridine ligand and the nickel chloride, this complex, it showed several redox peaks. The first one at about -1.7 volt, it is the nickel 2, nickel 1 redox behaviors. And here is another redox peak at about 2.5 volt. It is the nickel 1, nickel 0 redox. And finally, this one, it is the same as the ligand, so it is come from the free ligand. But when we add the arabromide substrate, we can see the current response is come from the first peak of the nickel complex. So we can confirm their oxidative addition is the nickel 1 based reaction. The second figure is the CV of the reaction mixture. The negative side, we can say the reduction of the nickel 2 to nickel 1 and followed by the oxidative addition. It is the same as this orange curve. But the positive side, we can say there is a very big peak here. Actually, it is the oxidation of the fluoroborate salt. This one can be oxidized, and the unset potential for the oxidation of that substrate is 3.3 volt. The third picture is the electrode potential monitor during the reaction. You can see during the reaction, the cathode side, the potential of the near to the, actually it is about this place. It is about this place. So that can tell us during the reaction, it is the nickel 2 reduction on the anode side, on the cathode side. But in the anode side, we can say the potential initially is at about 0.3 volt, and at the first stage, it dramatically increased to about 1.7 volt, and then slightly decreased and stabilized at about 1.3 volt. So because the positive side, there is only one reaction is possible. It is the oxidation of the borate. So we think it is the borate oxidation. But overall, we can see the cathode side, the overpotential is very small, and the anode side, the overpotential is much larger. So it can tell us that the overall reaction, in the electrolysis cell, the overpotential is mainly come from the anode side. Here we also started the cathodic carbon bromide activation. For example, under this standard condition, we use the anode, we use the porous glass carbon as the anode. We can get a very good yield, 93% of the desired CC cross-coupling product. However, if we use the zinc metal as the anode, under this condition, the zinc metal will be electrochemical oxidized, and the zinc stripping will be the anodic half reaction. This substrate oxidation will not happen. Under this condition, we did not get any of this CC cross-coupling reaction. Only the aerobromide is almost quantitatively converted to this CC homocoupling product. So that means the carbon bromide activation does not need the anodic oxidation half reactions. And here we also wanted to confirm the anode side is the radical formation in the anode side. So we did a divided cell configuration for the radical capture. For example, we use this divided cell, and the positive side, we set up the reaction, use the borate substrate and 3 equivalent of tempo. In the middle, we used ion conductive membrane to separate those 2 different cells. And the negative side, we use zinc salt and the sacrificial reagent. After the controlled potential electrolysis at 1.2 volt with the first, we can get 86% yield of this this product. Actually, that means the tempo can traps the radical, and the radical is rarely generated at the anode side. Here is the SEM study of the electrode before and after the electrolysis. We can see the porous glass carbon before and after the reaction are both very clean. The surface is very smooth, and we did not find any nickel metal on the surface of the glass carbon electrode. So that means the nickel metal does not deposit during the reaction, and it indicates this reaction is a homogeneous catalysis. It is not a heterogeneous reaction. And here is the CV before and after the reaction. You can see the green curve is the CV of the reaction mixture before add this area bromide. We can see the reduction peak here and the oxidation peak here, but the reversibility is poor. And the blue curve is the reaction mixture. Of all those components, we can see the current response is very strong. And when the reaction was processed in the halfway, it at 50% conversion. The CV showed up as the orange curve. We can see the current response is weaker. And when it was 100% conversion, this arrow bromide was fully converted. It is the green curve. But you can see the reductive current is almost the same as the original ones. And also the return peak showed a little bit. Yeah, that tells us the nickel catalyst is highly stable during the reaction. And it is also possible to use the CV to monitor the reaction process. So based on the experimental study of the reaction mechanism, we can propose a reaction mechanism like here. First, the nickel-2 species was electrochemically reduced on the surface of the cathode to get this nickel-1 species. And this nickel-1 can oxidative addition with the iron halide substrate to generate this nickel-3 species. This nickel-3 will be further reduced on the cathode to get this nickel-2 intermediate. And at the anode side, the borate substrate was oxidized and decomposed to generate a sp3 carbon radical. And this carbon radical can bond to the nickel through single electron transmetallation to generate this high valence nickel-3 intermediate. And this nickel-3 intermediate will undergo reductive elimination to generate this CC coupling product and also recover this nickel-1 catalyst. Yeah. So to summarize, in this study, we developed a electro-nickel dual-catalyzed redox-neutral CC cross-coupling reactions. During the development of this reaction, we use the CV screening to select the reaction substrate and the catalyst and also the ligand. We use the flow cell to demonstrate the large-scale flow synthesis. And based on the mechanism study, we confirmed that the oxidative addition is based on the nickel-1 species, and the anode side, it is the electrochemical radicalization happened on the surface of the anode. Yeah, here is all my reaction detail. We want research detail I want to share with you guys today. Yeah, thank you. Welcome for all the questions.
All right, fantastic talk. That's really cool stuff that you're doing.
Yes, thank you.
Let's jump straight into the questions here. Let's see. Okay, so in non-sacrificial systems, is back reaction an issue?
Let's go back to. I think in this page,
Yeah,
right?
I think it was referring to this slide. Yeah. So
Mm-hmm.
you show, yeah, like the type one, I think you have. So you have the sacrificial reactions. So there's kind of only one reaction. But in type two and type three, is back reaction of the, I guess, like substrate to the intermediate one. Is that an issue? Like going back the other way?
Oh, you mean for example, this one, right?
Yeah, so like if like going from or from in the type two one you have intermediate one or the substrate to intermediate one. Do you ever have an
Uh-huh.
issue with intermediate one being oxidized back to the substrate to start with, or is it pretty much unidirectional?
Yeah, I think it is one of the issue for this kind of configuration. For example, if the intermediate one is stable enough, and also this process, if it is electrochemically reversible, yeah, it is highly possible to oxidize back to the substrate.
Okay.
Yeah.
Okay.
Yeah.
Let's see. So why did 1.5 equivalents of the ligand give the most current?
Yeah, I think here.
Yes.
Actually, in the reaction mixture, the coordination of the bipyridine ligand with the nickel catalyst with the nickel metal, there is equilibrium there. So if you just add one equivalent of the ligand, for example, this is this blue curve. Actually, you will see a strong current here. This strong current actually it is the nickel deposition, because there's still a lot of nickel was not coordinated with the bipyridine. So when you scan to negative, the nickel will be directly reduced to nickel metal.
Interesting. Okay, so the extra the slightly extra equivalent is basically to force that ligand coupling.
Yes.
Interesting. Okay.
Yes.
Let's see. Okay, so this was a question I had talking about your flow cell. What type of flow channels do you use? Like, I guess what's the flow pattern on the blocks?
Oh, this actually it is just the graphite.
Okay. Do they have like channels carved into it?
Yes, inside there is a channel, but
Okay.
in the inside of the chamber, we also add a piece of carbon filter or carbon fiber to
Okay.
increase the surface area.
Okay, so you forced the liquid solution through like a carbon paper or carbon
Uh,
cloth to
yes, right.
increase the residence time.
Yes, actually the configuration is kind of like the fuel cell.
Okay, yeah, that's what I was wondering. Yeah, 'cause I do work with fuel cells, so
Uh-huh.
I was curious. Like I saw that cell and went, I recognize that.
Yeah.
Okay, very cool. Let's see, what type of separator, if any, do you use in that cell?
Yeah, in this cell, because we want the intermediate to generate at the cathode can quickly migrate to the anode and finish the whole reaction. So I use the dynamic membrane, and at the same time, I put a lot of small holes on the membrane.
Oh, you actually put a hole in the membrane. Okay,
Yes.
interesting.
Mm-hmm.
Okay.
Yeah,
Does the Go ahead.
we add the membrane is just want to physically separate the anode and the cathode to avoid the short connect.
Right.
But we do want the solution migrate fast, so we just put some more holes on the direct membrane.
Okay.
Yeah.
That makes sense.
Mm-hmm.
Let's see. Looks like we got one more question here. Oh, this is a good kind of general question to finish off with. So your work here talked about talked about nickel. Do you expect that there are other transition metals that could work in a system like this?
Yes, I think maybe cobalt, iron, this kind of transition metals can also work for some kind of substrate combinations. Yeah.
Okay. It does seem like a very versatile system. I mean,
Uh-huh.
it's complex and you have to kind of get all the pieces right, but it seems like that's relatively straightforward to do, which is kind of cool.
Uh-huh. Yeah, we just want to build up a general method
Mm-hmm.
for the development of the new reactions. It
Yeah.
seems like the CV screening
Mm-hmm.
can work. Yeah.
Yeah, I would say so. Yeah, I mean, I think you did a really nice job with the reaction mechanism study, especially where you kind of break down how you determine what the mechanism looked like by going through all the different pieces. That's really well done, and is yeah. And I know it's not easy, but it's easy to understand what you did, which is that speaks highly of how you delivered the information. You know, like I said, I'm not I've never done this before, but I was able to follow why you did what you did really well. So that's, like I said, that did a nice job explaining that. This is
Yes,
really
thank
cool
you.
work. I think that's all the questions that we have. So I will, if anybody wants to get a last minute one in, please feel free. But I'll go ahead and kind of start wrapping up. And if I could get you to hang around for just a minute, John, we'll talk briefly after this is over. But thank you to everybody for coming out. Thank you again to our speaker, Jian. It's like I said, this is super cool work. This is really
Thank you.
neat. I enjoyed learning about what you're doing, and I'm sure you will continue to produce really interesting results like this. Yeah. So thank you to everybody for coming out, and we will be back next week.
Yeah.
Double check and make sure. Yes, we will be back next week. So please feel free to come back out, same time, same channel, same day, all that good stuff. And we'll see you then. In the meantime, have a great weekend, everybody. We'll see you next week. Have a good night.